So quick poll to begin with. How many of you have coded anything in Go at all? Okay, awesome. So about half a dozen. That's perfect. That's a little bit more than last year. So we're on a good trend. So no, this talk is meant to be an introduction for the most part. So if you haven't, you are definitely in the right spot. So thank you for coming. So just really quick about me, why you may want to listen to anything I have to say. So I've been involved with Linux for almost 2 decades now, and I've worked around Utah. I'm from Utah. Had a few interesting jobs here. I'm currently writing Go basically 100% full-time for the last year, a little over a year. So the goal of this talk is to get you guys and any guys and ladies here, familiar enough with Go to reason about where and when to use it, and to facilitate you guys your guys' proficiency. So quick history. So before we get into the slides in earnest, I just want to say I gave this presentation last year, this introduction to Go talk. I got a little bit of feedback that I spent too much time on the syntax of the language and kind of the fundamentals. So I'm really going to hum through. I've reworked the slides. I'm really going to hum through these first few. If you guys have questions, let me know. Otherwise, I'm going to just kind of get through the boring stuff and on to kind of the neat features of Go. So quick history, though. Go has some big names behind it. Ken Thompson, who was involved with the development of Linux, or the Unix operating system. Rob Pike, Robert Griesemer. It's probably important to note also that doing research into programming language design was not a goal of the project. They wanted to make kind of an incremental step, a productive language. They borrowed from many different existing programming languages. So Go is very familiar, should be very familiar to you if you've ever programmed in any other mainstream programming language, like C, C++, Java, C#. And the basic justification for another language was the computing landscape had changed enough over the last couple of decades since Python and Java started that we needed a new language that compiled faster, that took multiple CPUs into account as kind of just a given. And the problem was, as the computers got more complicated, networks became ubiquitous, programming tasks became more complicated, and distributed systems started being everywhere. Programmers were choosing easy languages, relatively easy languages like Perl, Python, Ruby, JavaScript, over computer efficient languages like Java, C++. And their basic assertion was that needn't be the case. We can have both. So we'll start out from the really high-level view of what Go is. And then throughout the talk, we'll kind of drill down and hopefully in a path that leads us to some more interesting depths. So am I standing in your guys' way? I'm not sure how to do this. So Go is compiles down to machine code. There's no virtual machine. Strongly typed. In fact, it's very strongly typed. There's no implicit type conversion. Statically typed. It does something kind of like duck typing, though. So if you're familiar with Ruby or a Python, you get some kind of neat dynamic feel out of the language, which again we'll go into more in depth. And I need to start my timer here so I don't go over. Okay. There is a garbage collector, pass by value. It's similar to C, C++, those syntaxes, like I mentioned before. And it's open source. In fact, all of Go is now done on GitHub. The code's out there. You can create your issues out on GitHub for the language. They don't accept pull requests through GitHub. They have their own system for that, and that's similar to some other major open source projects on GitHub. But it does make getting involved really easy. And all of the proposals for the language and upcoming release proposals, those are all done on Google Docs. So you can get involved, you can comment on proposals, you can make your own proposals. So it's really, really open. So some things that Go does not have. There are no classes, basically no exceptions or assertions, no templates, generics, no operator overloading, no function overloading, no optional functional parameters, macros, implicit type conversions, and many other abstractions that you might be used to from other modern languages. So as a quick aside, the thinking here is this is kind of a constant in Go's design, that making things simpler will actually make things easier for the programmer, not only to write, but also for those that are reading in the language. So we'll talk a little bit about how you get along without these things. And if you want to get more in depth, I'm doing a tutorial here on Saturday where we'll actually sit down and do some code and have some tasks so you can get your hands dirty. Okay, so this is pretty small, but this is a graph of where Go stands currently as far as adoption of the language. So on the y-axis here, we have a popularity rank on Stack Overflow by the number of tags on Stack Overflow. So that's y. And on the x-axis, we've got popularity rank on GitHub by the number of projects. So that kind of gives you a neat idea. Go sitting right there. And then all of your kind of C, C++, Java, script, Java, Python, they're kind of globbed in. Ruby, C# kind of globbed in right there. Go is relatively new. Its 1.0 release was done in 2010, I believe. So that's when the language became stable, and it really started, the adoptions really began to pick up because people could count on their APIs not changing, and the language APIs. Companies using Go, so a little bit more about adoption. Last year when I gave this talk, I had trouble filling the slide. Well, I had more trouble filling the slide. This year I just had to leave many off of here, but there's companies like Apple that I never expected really. IBM, I met a guy at GopherCon last year that worked for Intel doing some Go. I don't even think I put that one on here, did I? Oh, there it is, over there, far away from me. And then there's some Utah-based companies. Well, SUSE is not Utah-based, but they have an office here. Rakuten is a company I work for, Japanese company who also has an office here. Space Monkey, they were a Utah company. They were acquired recently. Smarty Streets, they're in Utah. Weave is also in Utah. But really broad adoption. Okay, so this is a pretty common question, I think, of people looking at Go. Where can I use Go in the stack of technology? So I created this kind of spectrum of the technology stack. And on one end of the spectrum, we have embedded. This is real embedded software, no operating system, just running on bare metal. Go's not really suited for that case because it requires an operating system. It's garbage collected. It needs a runtime. Same thing for kernel. There are some people that have done proof of concept kernels in Go, but it's really not its strong suit at all. Basically everywhere here in the middle, you can use Go just fine. Library, the only thing that may inhibit you a little bit is a lack of libraries, especially for this commonly well-suited area. Third-party libraries for networking and cloud stuff, those are really they're available and they're really high quality. A lot of them are baked right into the standard library of the language. And we'll get into that. Front-end stuff, not so much. I mean, you're not going to be running it on your browser. But there is a Go4JS project for any of you guys that are interested in doing front-end and having Go across the entire stack of your web stack. Okay. So the next few slides I borrowed from one of the Go team's talks. Brad Fitzpatrick did a talk about Go, and it really resonated with me. The title was Go's 90% perfect 100% of the time. A little bit of an allusion to Anchorman, for those that have seen that. So the next couple of slides, obviously, we're going to be comparing languages. It's all subjective, and there's always trade-offs to consider. So again, we're comparing kind of languages that are fast and fun for humans to languages that are fast and efficient for computers. So fast languages like C and C++ that you would write an operating system kernel in, or a video game, they're sitting down in here. And then our fast languages for humans to write kind of sit in this corner here, like Ruby, Python. You can just kind of sit down and start writing. It's very English-like syntax, really easy to read, and write quickly. And then Go is kind of sitting here. It's really fast and efficient. I would personally, I didn't do this slide, I'd probably scoot this up on the fast and fun for humans axis a little bit, just because the more I've programmed in it, the more I realize it's really quite a fast and fun language to write. Okay, and then here it's talking about concurrency. So efficient concurrency in terms of performance versus currency that is beautiful to read and write on the page. And the assertion here is that Go is nice to write and read because they have some primitives built into the language to facilitate concurrency, which we'll talk about later. But it's also a compiled language, runs machine code, and so you get a lot of the higher performance benefits as well. Okay. So a quick breakdown of what I dislike about Go. First of all is the name. It's ungoogleable. If you Google for Go, you'll probably come up with a bunch of stuff unless you add some more context into your search. Pretty much everyone in the world and in the community is using Golang as a search term on Twitter, on Go. So I basically prefix all my searches with Golang. In fact, I find myself, the other day I was doing a little something in Python, and I typed Golang and then my question for Python. So that's how much of a habit it is to tack on Golang. There are some inconsistencies in the language that are kind of warts. Lack of generics can sometimes be awkward. It's a small language, but there's still too many things. There's just a few. I like just want to hum through these slides, but so I won't cover them all. But what I like about Go is that I almost never care about those things that I dislike. It goes back to that 90% perfect 100% of the time. Like, you get a lot of really nice things in a compiled, statically typed language that runs fast, and you get them almost for free in terms of adding more difficulty for humans to write and read. I wrote a lot of Python. Before Go, all of my kind of higher level code was all written in Python. And I like Python. It's a good language. I have lots of friends that are still using Python. For me, it's basically replaced anything I would have written in a dynamic language. In fact, I open a Python interpreter every once in a while to do some math or something, but it's really all I use it for. Concurrency is really easy. We'll cover that. You get your compile time checks, which is I forgot how nice it was after writing a lot of Python for so long. It is really nice to be able to have your static types and compile time checks. especially when you don't have to give up very much to get those. It's pretty fast. It's a very small language. I really like being able to compartmentalize the entire language in my head, and I can go into, I can kind of know, I can fit the whole language in my head, and it makes it easier to write and to read. It's got really good built-in tools also. So this slide, the obligatory wall of text slide, is basically just saying that when you're learning a new programming language, it's, even though it may borrow from some other programming languages, it's not the same one. And that you need to keep that in mind and really strive to know how to write idiomatic code in the language you're using. For example, don't try to write Java code in Go. Don't try to write Python code in Go. Even though I've known this, I've been developing software for a while. When I switched from C and Python to writing Go full time, I was still trying to do lots of object-oriented things. Like I would think about inheritance, and I'd be like, okay, I need my base type. I want to inherit this, and there are some object-oriented things in Go, but if you try to just port like a language into Go directly, you'll experience some difficulties. The best way to figure out the idiomatic Go, we're going to do that on Saturday. We're going to actually write some code. We'll cover it a little bit today, but it's open source. The libraries are really easy to read. If you have a question on how to do something, just open up the source code, check it out. There's not all these layers. The source code really is very approachable. Like Python, it's not like, oh, is this going to go into C Python land? Am I going to have to go in and read figure out how it's doing all this reference counting and everything like that? Really, most of the standard library is very, very easy to read. Okay, so finally, we're to code. So this is a basic Hello World package, Hello World program. You have to specify your package on the first line of code. You do imports, just like includes. So another quick poll. How many of you come from more of a dynamic background like Ruby, Python-ish, JavaScript? Okay. How about more of a C++, C, C#? Okay, awesome. And you could raise your hand for both, obviously. So good. That's about half and half. That's good. So I think Go, it really is a good compromise between those two philosophies for the problem domains where it works well, like in that spectrum that I had up. So UTF is built in. It's a first-class thing. You declare a function, main, print. Pretty easy. Everybody else seen? So strongly typed. Here's your basic types, just to give you an idea. You got bools, ints. You've got your sized ints and uints. Yeah, so that should all look pretty familiar. And type declarations. So here on the first line in main, we've got a simple type, some simple declarations where we say we have I and J. They're both of type int, and we do our assignment. So that's one way to do it. You can also use the := syntax to do type inference. So now K becomes it's defined there. It's declared and defined, so it's actually allocating the storage and doing the declaration there, and storing it in K, and now it's in scope. And K becomes a float because it can infer the type. And then here's just some other types of inference. You can do the inference of multiple types on the same line. So we got bool, string, and then a one character or single quote guy here is actually called a rune in Go. We won't go into runes that much because it's a little bit more of an intermediate topic, but just you can kind of think of them as characters. And it gets into the Unicode part of the language. So some more basics here. Looping. if else, switches, and const. So const just says to the compiler that this guy isn't going to change. You can and then looping is pretty familiar if you've ever done a loop in C or C++. We don't need to talk about it too much other than to mention that the for loop is the only loop in Go. That's the only keyword for looping. You can omit different pieces of this for loop, but to accomplish a while loop or a for loop, you will use the for keyword. Or to loop forever, you just type for. You just omit everything. So it's kind of a neat example, I guess, of just how much they tried to simplify the actual language syntax. So, and then a switch statement. If you've seen one, you've seen them all. So, okay.
The cases don't drop through.
Correct. Yeah, good observation. The cases do not fall through unless there is a fall through keyword. So you can actually add fall through if you want. Whereas in C, you would have to add a break. It's just reversed. The common case is you want to break. So yeah, that's in my experience anyway. Structs. This is how you create your own types in Go. There are no classes. You have structs. So here is a struct with X, Y, and Z, 3 ints and a string. This is how you instantiate a type. And I don't expect you to memorize this all. These slides are available. I'll give you a pointer to these. But here's instantiation. And then all I'm doing here is printing out using the printf function in Go to print out these values in different ways. So you use interpolation much like C. Like if you want to print out a string, you use %s. If you want to print out a number, you use %d. And they're like here. And then there's a few more. %v tells Go just to print it out in some human readable-ish way. %pound_v, and you can look these all up. There's a bunch more, but it just says to give a Go syntax representation of the value, and %t will actually show you the type. So I'm going to actually run this code here, and you can see what some of these do. Oh, great. Dun, dun, dun. Whoops, went too far. Okay. So actually run the code, and you can see it's printing out this coordinate object. Print line will actually print it out the same way as printf with a %v. %pound_v will actually say, oh, that you're in package main. This is a coordinate type. Here's the fields and their values. I use %pound_v a lot in debugging because it's really nice to see exactly the type, all of the information there. %t will just print out the type information and so on. Name, here it's an empty string, which you may notice that I just omitted it in the instantiation. So the things that you don't specify start out with a value. They don't, in general. I guess I'll just say that the default value of a type in Go is the 0 value for that type. So 0 value is a Go term. The 0 value of a string is an empty string. The 0 value of an int is 0. The 0 value of a float is 0.0. It gets a little bit trickier with more complex types. The 0 value of a pointer, for example, is nil. So you do still have nil pointers. You still can have a nil, but for a lot of your basic and built-in types, they'll default to a 0 value that is actually usable. Yeah.
What about the 0 value for a bool?
The 0 value for a bool is false. Yep. Okay. So just as an example of 0 values, if I was to here type var foo int, and that's it for that line. I would now have an int defined that was 0. So also when you do object instantiation, it initializes all the fields to their 0 value if they're not specified. Okay. So I just mentioned pointers. Go has pointers, but they're not as scary as in C. So if you're coming from a more dynamic language, don't be afeared. They're really not bad. In fact, you often don't have to think about them other than to know that when you pass an object in as a pointer, it can be mutated. And that's similar to a lot of your dynamic types anyway, like maps and dicts and lists in Python at least. So so here's an example. Got this coordinate guy again, and I actually created a constructor for him. This is the idiomatic way to write a constructor in Go. It initializes these things, but it's actually returning a pointer to a coordinate. And then I do some printing out things again, which isn't very interesting. You'll just see that now it's a pointer to that thing instead of the thing. In C and C++, if you're coming from that world and you have a pointer, you would be used to doing essentially this, but instead you'd be using the syntactic sugar arrow, right, the dereferencing operator, which is effectively doing a dereference and then indexing into the member, referencing the member there. So if I wanted to call coordinate.x, I have this object. I call could dereference that and then call x, and that would work. But you don't use that in Go. You just use the pointer. You call the member, and so it looks very familiar, very very simple. Yeah.
Does that mean all structs are pointers in Go?
No, they're not. In this case, you see we're returning actually the asterisk, which indicates pointer. Sorry, I forgot to mention that. So here we're actually returning a coordinate pointer. Back a couple of slides, or just one slide, when we did this here, coordinate there is just a struct typed. Yep. What you can see here actually when we printed out the type. To compare that, if I run this one, you'll now see that the type is of pointer main coordinate there. So okay, cool. Slices are like lists, or vectors. I don't want to spend too much time on them. Maps, hash maps, or a key value data structure, dict, like dict in Python. They're used in a similar way. When you, let's see, okay, I guess this is kind of an interesting thing. When you are trying to retrieve a value from a map, you will use your map here, and then the value, the key for the value you want to retrieve, it will return a value and a bool. And this is called the comma OK idiom. So we're getting the value and then comma OK. OK is telling us whether or not the value was present in the map. So you do have to check that. V, if it's not in the map, it will return its 0 value. It'll return the 0 value of the type of the value in the map. If that makes sense. Okay. Functions are first-class things. Here I'm just showing an example of a var, a variable that is called double func, and it is of type func that takes an int and returns an int. And then I'm assigning it here to a func that takes an int and returns an int. And then you can just call double func and get a value. Or you can actually just define it, declare it, define it, and call it all here in line. So print line, func, takes an int, returns an int, and then call it, and got that. So this is one of those things, kind of the special cases of, I guess, maybe a little bit of an inconsistency in Go. There are maps, slices, and channels in Go. We talked about maps. Those are your dicts. Slices are like lists. We'll get to channels. They have to do with concurrency. But these things act like references, basically. Essentially, they are a struct, but the first member of that struct is a pointer to the actual underlying data. So anytime you pass these around, they're getting passed by value. They're getting copied and passed by value. But it's just a little metadata, I guess, about your data. And so the important thing to remember is as you pass these types around, they'll actually mutate your data, which shouldn't be too much of a surprise if you're coming from a dynamic language like Python, that if you pass a list or a dict around, you're passing around a reference to those two. Kind of an early mistake I see Go programmers make is having pointers to maps and slices and channels. It's not necessary because they already act like them. Okay, so methods. Okay, great. We've got our types. We've talked about structs, and now we're starting to add methods onto our objects. We're creating member functions. You do this using the syntax called a receiver. So this portion right here between the func keyword and the name of the function is called a receiver, and that's how you identify a method. So this double func is a method on point. So down here we instantiate point. We call double values our method here. What would you guys expect to be printed out? Anyone? You might expect that. I will run it. 2 and 4. And this is a little bit of a trick, or I guess a common mistake when you begin also. The reason is we created a new. Does anyone want to take a guess at what the reason for that is? Go ahead. Exactly. We created a struct. It is not a reference type. We reference like type. They don't really like. The community doesn't really use the term reference type, but it's an easy way to think about it. We created a point, an object. It's not a reference like type. We passed it in. It passed it by value, copied the struct. Inside of here, it doubled those values, but when we got back out to here, the state wasn't mutated on our original P. So if I go into this code and make this receiver a pointer receiver and rerun, now we'll see the 4 and the 8. So the easy way to remember, the first thing to know is usually you want a pointer receiver. So as you're writing, you can go ahead, create a pointer receiver, unless you can make some justification for why it shouldn't be. There are a lot of instructions on when and when not to use a pointer receiver. It's another 90% of the time it's totally fine. 10% of the time it's a bit of a headache. Go ahead.
So does that mean by default it always passes by value?
Yes. Everything in Go is passed by value.
Are there ways to pass by reference if you want to?
You will not in the same way that C++ does. Instead, you'll just pass a pointer. And that's how you pass. Yeah. So, for example, passing by. When this method's getting called, basically P is just getting passed in to this function in just a little bit of a different way. So here we're passing in as a pointer, and that's kind of our way of passing in a reference to that. So there's more information on receiver types, but that'll suffice for this discussion. You'll hear people say that you can create a method on any type in Go, which is mostly true. You can't do it directly on built-in types. So if you wanted to create a method on a uint8, for example, you have to do a type def, create your own type, and then add on your methods. And you can only add on methods for types that, you can only add on methods for types that are defined in your package. So you can't go take somebody else's type and start adding on methods to it. Okay, so polymorphism and inheritance review. So this is really kind of where Go starts diverging from other common languages. So polymorphism, just a refresher, is the ability for one type to stand in for many different types. So in most statically typed languages, I'll take C++ as an example. You have a base type, like let's say you're doing a grading system for a college. You've got a base type that's maybe student, and then an inherited type that's grad student, we'll say. So if you have a student type as a function parameter, and that it's a pointer to a student or a reference to a student, and you were to have a grad student and pass it in, it will use polymorphism. I mean, you have to have everything set up properly, but it will basically treat your grad student like a student, and so you can have old code calling your newer code because it's treating grad student polymorphically. So, and then you're also inheriting all of the implementation from your student class. So, I mean, it's a whole other topic, but switching to dynamic languages, they provide polymorphism generally with duck typing, where you just pass in whatever value you happen to have, and hopefully it gets used in the correct way. It'll just start calling functions on it. If they're not there, you'll get a runtime error. And inheritance in dynamic languages is used for borrowing implementation from the base classes. So Go separates these two things: the polymorphism and the implementation borrowing. They're decoupled. So Go provides polymorphism using interfaces, which we'll cover, and it provides implementation borrowing via embedding. So there is no direct inheritance in Go. So we're going to talk about both of those real quick. So embedding is taking we have a type here, a struct, and then we have a new type cow struct, and you'll notice that here for is female, you've got both the name of the variable, the member variable, and the type. Here we've just embedded this entity into cow, so now it becomes it borrows this implementation. So now basically it has an ID and a size, and you can call c.size, a cow.size, directly. So you just call c.size, you assign it, and you'll notice cow doesn't really have a size directly. It's borrowing it from entity. Does that make sense? I'm going to try to hum through these ones because we're getting close, and I want to get to the concurrency stuff. So skip that. Interfaces. Interfaces are super important in Go, and they're one of the hardest things to pick up and become proficient in. They're a little bit more of an artistic thing in Go because it's how you construct, or forgetting the word, but it's basically how you build things that interoperate together. So here we've got a talker interface. So it's very idiomatic in Go to have interfaces with just one or two methods that end in ER that describe what they do. So here we've got a talker. This interface says has a talk method, and what the interface is saying is to implement me, you have to implement a talk method that takes no parameters and returns a string. If you do that, you're a talker. So now I've defined two types, cow and fox. They're actually empty structs, which is another interesting topic in Go, but they're basically types with nothing in them. But I can just start adding methods on them. On fox, I've added talk. It returns a string. It implements the talker interface. Now I have a function ask. It takes a talker and asks what it says this thing does, and it calls the talker.talk method. So you notice Fox doesn't implement this method directly. I mean, it does. Talker doesn't implement the method directly. It's just saying this is what you need to be a talker. And then on main, I'm calling ask on cow and on fox. And as I run this, you'll notice I'll get a crash, and it tells me exactly why. It says, great information, cannot use cow literal type cow as talker in argument to ask. Why? Because cow does not implement talker method. And it tells you why it doesn't implement it. It's missing the talk method. So this is how you achieve duck typing-like behavior in Go. And it's actually a compile time check, which is super, super nice. Like in Python, you implement your dunder, all of your dunder functions are methods on a type. Sorry if I'm using, Python's what I'm most familiar with, but Ruby, hopefully you guys can relate. You implement some special magic functions on a class. And I think Python actually just calls them magic functions, or magic methods, and you pass them in, and the receiving guy tries to call them, and if they're there, it works. If not, you blow up. So it's nice to have the compile time check. So again, I'm going to skip the real world stuff. You guys can look at these errors. Errors in Go are kind of fun. They're their own thing. The error type is an interface. So the basic thing is if you implement an error, if you implement your own error function that returns a string, you're all of a sudden an error. So they're an interface. Concurrency. Okay. So skip that one. Let's go to this one. Go has a built-in keyword called Go, and it's it's referred to as a way the second word here is a function, and it's called a Go routine. When you use the Go keyword, you feed it a function, it asynchronously executes, and you'll notice if I run this here, which is basically just repeating a bunch of strings. If I run this right now, nothing. It just exits. And this isn't the same problem I was having before, by the way. What happens is we've run go repeat. We've run go repeat here, and then we got to the end of execution. The process exited, so we didn't get to see anything. So Go introduces a language type, a primitive called a channel. So what I'm going to do is I'm going to add another parameter here. I'm going to make it name it ch. It's a chan of type bool. Channels are typed. So, and then what I'm going to do here is create a channel 1 using the make function, and a channel 2. So I've got 2 channels. I'm going to feed them in through here. And then when I'm done doing this sleeping and work here, I'm going to send the channel something down through the channel, which is, I'm just going to send true to the channel. And I'll explain what this is doing when I get it done here. And then here I'm going to read from channel 1, and then I'm going to read from, there's my semicolon, channel 2. Now when we run this, unless I mess something up, okay, we'll actually see these things being printed out asynchronously. Channels are a way to communicate. So this is a whole other topic in Go. Concurrency could be its own talk easily. But it makes it really, really super simple to do concurrent things. The channel here, when it writes in when true is written into this channel, execution blocks on that Go routine until something reads from that channel. So it's also a locking mechanism to avoid problems there. So I think I have another example where we can use buffer channels. Buffer channels are like channels, but you can feed multiple things into them before something needs to be read out. So here I've got a channel that takes 2 things, and it's an int channel this time. It's of size 2, and then we feed in 1 and 2, and then we read them out. So it prints out 1 and 2. If I was to change this to a 1, so now it only accepts 1 thing, which is basically the same thing as if I did this, and I run this, I'll get a runtime error saying that we have a deadlock. We route 1 thing into the channel, and then there was no other asynchronously executing routine to read anything out. So this next line can't execute because it can't put another thing into that channel. So buffer channels. Select is a super handy thing where it will actually check to see if which of these cases becomes available first. So if you have multiple channels that could possibly receive, you can do case statements on your channels, and the first one to become available, it will execute that way. So it's sort of like the select system call in Linux, where you're monitoring a file descriptor, and when it becomes available, you can use it. Some real-world concurrency. These are okay, and here is an example of a fully functional web server in Go. So you got a package main, you use the net HTTP standard, it's built-in library, it's extremely useful, extremely well done. Normally, a lot of people coming from Go, this is probably worth saying, a lot of people coming to Go from other languages always want to know, well, which web framework should I use? What's available, what's out there? There are some, but pretty much anyone that's done a substantial amount of Go will tell you to begin using just the built-in net HTTP library and use that until you can justify using something else. Currently the place where I'm working, we have many high-performance web servers running, and we only use the standard library. Here's our main. We're just saying we're going to start the server, and we say HTTP handle func. So we say when we get a web request that's doesn't have a path, that's to example or foo.com, and then we handle it and send it to this guy here, and then we listen and serve. So if I run this here, I haven't actually, no, it crashes apparently. Oh, I know why this is. I'm not hosting it locally on my machine, but this will have your web server, and you have your response writer and your request. Your request will show you what the method was, what the path was. You can use it to do your routing. You can, like in a if else or a switch statement, you can, yeah, go ahead.
So does an HTTP handler have to conform to a specific interface, like where it accepts the response writer and the request? Is there like an interface that specifies?
Yeah, that's a really good question. Handle func just takes a function, takes a typed function that takes a response writer and a pointer to request. So it's not actually an interface, it's just saying I need a function signature that looks like this. However, there is an http.handle function, which we will actually implement on Saturday, or http.handle method. And handle takes a HTTP handler argument, which is an interface that you have to implement to be able to handle the HTTP request information. So I think I'm about out of time here. Another great thing about Go is the built-in tooling. You've got Go test. You can see your test coverage in a graphical manner. You can run go test-cover. It'll print out your test coverage %. It compiles and builds and tests all really quickly because you're in a compiled language. You can send an HTML flag to one of the Go tools and send it your test coverage output, and it'll actually bring up an HTML colored document showing you where your test coverage is and isn't. And you can do this all just within a couple of seconds. You'd see, oh, this red line here in my code isn't covered. I need to go in and add a test case for that. A few common mistakes, if you want to check those out. Some useful links. We host a Utah Gopher user group for Go at the office where I work. The Gopher Con in Denver is coming up in July, and it's a lot of the Go team is there. It's a cool place to be. This is a little advertisement. I have some flyers up here if you guys are interested in taking them and putting them up places or just to remember whatever. And that's everything.